Thank you for attending our talk on procedural map creation from sensor data. My name is Joey Kowalewicz, and I'm Ambrosiussen. And we are with Applied Intuition, an autonomous vehicle simulation company. So what are we going to be going over today is what is sensor sim, primarily off-road, world generation, and then future work with Gaussian Splatting techniques. So what is sensor sim? Sensor sim is one of our tool sets used by 18 of the 20 top vehicle manufacturers to safely test and simulate edge cases for autonomous vehicles. Here's an example of one of our edge cases where we can take say a simulation of a semi-truck and put it in a various number of environments, snow, fog, rain, and test it over and over again safely before we actually take it to on-road trials. At the top is an example of, we could change the actual material attributes, reflectivity of a tanker vehicle as the camera approaches to make sure, the cars stop. So our tools, we do work with on-road and off-road. There's a number of on-road and city-generated worlds already. So today we're going to be primarily talking about how we handle off-road. So utilizing lidar, there's two main types of lidar that we primarily use. The first one being aerial scan. So utilizing drones or any other fixed-wing aircraft gives us a quick view of a large area, lets us make a very large map very quickly. The downfall is, the terrain can be obstructed by foliage or other obstacles, depending on the type of hardware used from the lidar. The second is actually utilizing a drive scan. This one's pretty cool. So we actually take our lidar sensors and attach them to vehicles driving on off-road terrains. It lets us to recreate the exact path that a vehicle was just driven on. And you get some pretty high precision because, you're picking up a bunch of data from a very close area. So the typical flow chart is, we take the input data from a client, we pre-process it. I'll go over that in just a second. And we split it off into two sections. So we have our lidar automation, which accounts for about 90% of the entire process. From there, it'll split out to generating the terrain, instances, and whatever else we can do procedurally. And then the other 10% that we're currently working on, still automating, is the bespoke geometry that will just spit out as static meshes that will combine back in with Unreal. Let's see. So we work with a lot of data, so we want to work to scale. And so to handle, the dense point clouds, the dense data that we get in from customers, we decided that we need to tile and utilize PDG to reduce, workload, especially while we send our process to the cloud. It can work on smaller chunks at a time. It helps artists to troubleshoot smaller sections. They can isolate individual tiles, work on that, fix, update anything that may have not worked on the first run through. And it allows, for scale, for us to generate these large scale maps. I think one of them that we've done is like 140 kilometers. So the more clients we get, the more problems we get. Data comes in all, shapes and sizes. My favorite being that, the other day I got a text file of a lidar document. Luckily, we have tools like Python. And the integration with Python and Houdini allows me to either decide, hey, I want to actually convert this to a lidar file, import it with the lidar import node in Houdini, or I can just create the points with a Houdini Python sub. Really just depends on how the data comes in. All right, so now we can get to the terrain generation. So to start with is we take our lidar data, and we need to extract a ground plane. This is the most important part about off-road generation because we have to have a ground plane that is accurate to the point cloud that can be driven on. Something that doesn't have too much noise, not too much spikiness. It needs to be smooth where it needs to be smooth. It needs to have the ruts where it has the ruts. So what we do is we start by clustering based on normals. So we get this initial cluster, and essentially we're using an infection algorithm that'll just look to its neighbors and say, hey, are you like me? Are you within a certain threshold of the dot product? So we get these nice little compact areas, and you can see here, like in the trees, you'll see that the image, stops growing. So it's a good first pass, but it only gets us so far. We can't really isolate anything from that yet. So we can go to the next slide. Yep. So we take those initial clusters, and then we do something very similar. And so each cluster has an average normal position. So same thing. You find the neighbors, and you say, hey, are you like me? And eventually, after a number of samples of running this over and over again, you get these nice large areas that you see here. And we can now decide, hey, now we have large areas. Let's remove any clusters with too few points. And then you can create a best plane through that and remove any points that are away from that plane within a certain threshold, and that helps to remove any noisy points. So we have our point cloud. What do we do with it now? Now we need to project a terrain. So we do utilize HIVE, but we do it a little bit differently. We don't just use a HIVE project. We always could. It would be easy. It wouldn't be difficult. But instead, we have a couple tools set up that allows us to sample the point cloud within a specified radius. And the reason for this is being, you can't always guarantee that LiDAR data is going to be accurate, that it's not going to have noise. So we still need to find an average. So this, lets us do things like, hey, is this picking up a tree by accident over a road? We don't obviously want to average something that has a point maybe like, 3 meters high when, the road's not. So that gives us a nice terrain within 2 to 3 centimeters of accuracy in areas of interest and where data exists. That's the most important part. And then obviously there's always cases where you don't have data. You can't see, or the vehicle can't see, the drone didn't pick up, whatever it may be. So we would always fall back to using satellite data at that point. And you can see that here in the top right corner. It's much blurrier, much less detail, but we fill that in with post-processing afterwards. And so we move on. We have the road, and this is all the typical, game stuff, VFX stuff. We add the roads. The roads are very similarly projected as the terrain. The one difference being that the UVs need to be accurate because we need to tile a texture on them. So we need continuously flowing UVs. And then adding foliage instances. We can actually utilize the point cloud for this. So taking the point cloud, isolating by color or height or whatever method we need to use. And then we can then project it down to the ground, find the distance to the ground plane, isolate based on that, and then kind of safely make some assumptions that we can instance certain tree types or foliage types in certain areas, giving us a pretty unique and realistic instancing. This is, like I mentioned before, a pretty highly automated process, about 90% automated currently. We do have other tools to help create that other 10%. In the future, we are working on machine learning models to kind of automate that final 10% for us. And so here's, some imagery of the final output from product. And so this is, some of the roads or off-road that the vehicles would actually be simulated on.
Cool. All right. So the next part of the presentation, I'll be talking about a product that Applied has as well called a Neural Sim. And so what we saw previously, what Joey is presenting, is essentially your traditional typical way of reconstructing real-life scenarios in 3D and Unreal using Houdini, where the geometric accuracy is the highest importance, right? Because, for example, when you're simulating radar, lidar, other sensor models, those really need the geometry to be very accurate, right? Like the 2-3 centimeter accuracy Joey is talking about. Now, there are, however, other cases where you have different things that are important for your simulations when you're simulating sensors. For example, visual accuracy. And so that's what I will be talking about. So here's a quick little video that talks about what Neural Sim is. It's an actual product. Essentially, we automatically want to generate 3D realistic worlds from purely imagery, our lidar and other sensor data that we get. So what we see in this video is a street near where I live in Eindhoven, where this is a 3D reconstruction of a scene that has been made purely off of imagery from a camera that we've made. So it's a process very similar to, for example, photogrammetry, but it's done a little bit different, which allows us to get a lot higher quality result. Now, this, of course, works in various environments. We've seen one in sort of like a, pretty plain street. This one is a bit more complex because we can see it's a very dense urban environment, but it's not limited to on-road. It also does off-road, which is what we see here. And this is actually the same environment that Joey was showing previously, where we generated it synthetically. And so as you can see, it's fully 3D. You can fly through it, and it allows you to render it and do other things with it. So here is a California parking lot, the actual office of Applied, or old office really, which then can be used in a synthetic environment where you can actually simulate what happens in that environment. So for example, you can add additional actors, cars that previously weren't there that you want to simulate, where for example, you have a simulation where you want to test, how would my car have behaved if a car was parked there? Or what would have happened if, for example, a car suddenly pulled out of a parking lot while my car was trying to park itself? Those are all things and scenarios that are extremely difficult to capture in real life, but you are able to replicate at any scale, any scenario you can think of in a synthetic digital world. So that's essentially what this and the other product do as well, and allow the, for example, automotive companies to simulate. So how do we make this type of 3D scene that we saw before using Gaussian splatting? Well, the first thing, of course, is data capture. You need data to produce more data, and so that's what we do. And there are various ways of capturing this data, as I mentioned before. One of them is using imagery. Now, imagery can be captured from, for example, a vehicle, where you have a car that has cameras mounted on it that simply drives around and captures everything that it sees. For example, 8 cameras. We all have seen cars that have, parking sensors on it, for example, but there are certain car brands that have, even more cameras on them, which capture everything. The other method, of course, is using a 360 camera, for example, where you just walk around a street and you actually capture it. And in this presentation, I'll be going through a scenario where I show how to do that, because I can't quite show the proprietary capturing methods for cars themselves. You can also, of course, use lidar as a data source, because when you do Gaussian splatting, you need a point cloud for initialization, as we'll see in a bit. Now, that as well, you can also capture from vehicles, as well as, for example, from drone, or just get any other generic point cloud. So capturing a 360 video, what does that look like? This is what it looks like when I capture it. I recorded this here in beta. I always get people looking at me like, what is that person doing? No, I'm not a vlogger. I'm just capturing some data for some experiments I'm doing. But this camera itself, as we will see in a little bit, allows you to capture a full 360 view. And so what does that video look like that you get out of it? It actually produces this. It's a video in the equirectangular projection, which is the exact same projection format that, for example, the world map has when you look at it in the typical map. And we can see that it's full 360. I can see literally everything around it in a single view. It's made from 2 fisheye lenses, which are present on that camera we saw before. And we can see that we have significant distortion around the 2 poles, the bottom and the top. And those are things that we need to deal with or either discard. Now, in our case, we're not really interested in the sky, so we can just ignore that. But for the ground, we do need to do some work to essentially stitch that back into it being a usable format, which we will also see. The other method I mentioned, of course, is lidar, which allows you to capture point clouds. Now, one such method of capturing lidar, as Joey mentioned, is, for example, using a drone. Now, here we see one such example of a drone that has a lidar sensor on it. And on the right, we can see what such a lidar scan looks like for a single frame at any given time. We can see that it is fairly dense for a single frame. So if you do that over time in an area, you get an extremely dense and accurate lidar point cloud you can use. For the lidar and point cloud, it can either be captured, once again, aerial, right, with a drone, but also be captured on a vehicle. There's also cars that have actual lidar sensors on them that just capture everything around them continuously, which gives you a very accurate and high precision capture of the environment you're actually driving in, a street, a city, the world, really everything you want to do. Now, these point clouds are 3D geolocated, which means that they have positional data in them. You know exactly where this is in the world, which you can use in your reconstruction. They're also extremely dense, which is good. That allows us to filter down to something more usable. It contains color information, which is useful for initializing our scene, but it also potentially has other attributes, such as, for example, semantic labels, which means, hey, this point, what is it part of? Oh, it's part of a tree, or this point is part of a car, or this point is part of the road, for example, which is also useful because then you know what you're actually dealing with instead of just looking at points in a 3D environment. Once we have captured our data, images, lidar, other sensor models, we need to pre-process it because we can't just push it into a trainer that we've built for creating Gaussian splats. We need to prepare it first. Here we see some of the data sources that actually go into Applied.js, which is the trainer that we use to generate these Gaussian splats. And we can see that we take in images, we take in depth maps, and these depth maps are estimated from actual ground truth RGB images. We can take in lidar or other potential point clouds, generic point clouds. We then do structure for motion if we need to, so if we don't know where those images were taken. And that then produces in and extrinsics, which I will cover in a minute what that means. And all of that goes into the model, which then generates and reconstructs this 3D scene that we've seen before. So we saw that video from the 360 camera, which gives us an equirectangular projection. We can't actually use an equirectangular projection in Gaussian splatting. We need to use something called pinhole images. And pinhole images essentially have almost no to no distortion in the images themselves. Because when you have a camera, it has a lens, and a lens is curved. And the reason the lens is curved on a camera is so that you have a much larger view than the actual width of a sensor that captures the actual data. Because otherwise you'd have a super tiny picture and you only see a very small thing, but the lens curves that, which is what we need to account for when processing. Now, the 360 camera, of course, has an extremely wide lens, and that's why we got those projection issues we saw before. So in a shader, essentially what we're doing in theory is we are just simulating 4 cameras for that single frame, where we project that image onto a sphere and then capture individual box faces from it, so that we get, a capture as if we just had simply taken 4 pictures like that from the 360 footage before. Depth generation. So, like I mentioned before, one of the inputs we also use is depth maps. And depth maps can be visualized as essentially float scalars, right? They're actual values that describe, hey, this is 10 meters from you, this is 50 meters from you, this is further from you. So we can generate these automatically from purely RGB images. We don't tell it anything about where this is, what it is. It simply generates these maps for us. One of the tools that we've also built is essentially this viewer, which allows us to, for example, load these depth maps as point clouds and visualize them in 3D space, so that we can verify that those 3D point clouds generated from an estimated depth map are actually accurate. Because if you're feeding the model depth maps that are not accurate, yeah, the reconstruction also isn't going to be accurate. So visualization and debugging what we're able to do in 3D when doing training is very important for us. Now, I mentioned that we're estimating these depth maps, and that's great because then we don't need to go and have lots of scans and measure where and how far these are. The problem, however, is since we're dealing with depth map estimation, we're dealing with estimation, right? So if I take a picture here and I ask it to estimate for me, how far away is that? It may say, 3-4 meters. But if I move over here and I take a picture, it may say, oh, it's actually 5 meters, right? And that's a problem because we need to align these depth maps and RGB images in 3D space, so it needs to be accurate. So the very first thing we do is we actually take those depth maps and we remap them in 3D space based on some ground truth, right? So we take our depth maps, we project them in 3D space, and we remap that so that we fit all of the different ranges that we get into the same space. So that when we align them, we can see that we get something we see on the right versus what we would get if they weren't remapped to the actual absolute values on the left. The next thing we need to do is create some masks. And this is sometimes a manual process. This is sometimes an automatic process. We have models that allow us to automatically mask things like people, cars, whatever else. But for this demo, since I can't show that, I've just made a mask manually myself off of 2 data sets. We can see that when I capture this data, I don't need to be present in the reconstruction, right? Because I'll be present on literally every single spot on the road. We don't need that. But we also don't need this person in the reconstruction because that would simply cause artifacts and we'd have this person just stand there, which isn't quite useful in simulation. So we mask those so that we can tell the model, hey, we don't care about this thing, just ignore it. Now, camera in and extrinsics. We've seen that before, I've mentioned it, but what is it? Camera in and extrinsics are either derived from sensors on the vehicle itself, right? Where we know the actual transform of where is this in the world and where was the actual camera located when we took a picture or made a video. And we need to know that for every single picture relative to each other so that we know where that is in 3D space. Very similar to photogrammetry, for example. Intrinsics describe the camera distortion coefficients, focal lengths and principal points, essentially describing what is the distortion that is present in the image that we've captured, because we essentially need to remove that, as I mentioned before. And then the last input is the 3D points, which is a triangulated 3D point cloud, either derived from the structure from motion process or from 3D point cloud, for example, lidar, or another source. And so those are initialization for the training itself. So to visualize the camera intrinsics a bit more and understand how that distortion looks like, here we see two pictures. The left one is distorted and the right one is undistorted. And as you can see, due to the fact of how images are captured using lenses, the scene itself, you can see that it has curvature to it, right? Like those lines you see under the car for the parking spots, those are curved. But in real life, when we see it, it's not curved, right? So we need to make sure that we remove that so that when we align images in 3D space, everything also lines up, because otherwise everything would be warped and distorted and you get a lot of shifting and other issues. So we need to undistort all of the images based on the intrinsics of the camera that we've captured it with. Then once we have all that data, it goes into the Applied GS trainer, where we actually generate the Gaussian Splatting 3D reconstruction ourselves. I can't go into too much detail of all the specific nuances that we've made compared to sources that are out there, but I'll be talking about what it is and how it works. So to train a splat, the first thing you need to do is initialize a scene. And as I mentioned before, initializing a scene, we use the poses. And poses essentially are those camera extrinsics. Where is the camera located? What is the orientation of it? And so forth. We also, of course, use the point cloud because we need to start with a point cloud that we use for initialization so that we have something to start from. It's not strictly necessary to have this, but it very much speeds up the reconstruction time that it actually takes to make this. And last but not least, we of course need the images because eventually we are optimizing the result of what we see for the 3D splat and the images that we use to train it with. So then we go into initialization, right? We have our point cloud. What do we do with it? How do we make actual Gaussians out of it? In Houdini terms, this simply means we take that point cloud we saw and we attach disks to it that have a volume, right? So it's not just a flat disk, it has actual volume to it. Every point has a position, it has an orientation as a quaternion, it has a scale, it's a vector 3, because remember, I said it's a volume, and it has colors to initialize with. And in the beginning, it simply has a single RGB color, but later on during training, it will actually get converted to something called spherical harmonics, which are view-dependent colors. So the color changes depending on how you look at it or from which angle you look at it. And then we do the actual training, right? So this is just draw the owl, where we have our ground truth image, which is the one on the left, and on the right, we can see the actual reconstruction at real time, reconstructing the image on the left. So we essentially simply take that point cloud that we initialize with those disks, and we inject noise to it continuously to modify all of the attributes in Houdini, essentially, so that they appear when rendered in the format that we see on the left. And we do this thousands and thousands and thousands of times using a regression model until at some point, all of the points essentially have the right attribute values so that when rendered, appear as if they look like the left image. And since you're doing this with all of the images and poses in the 3D scene, you get a 3D reconstruction, right? Because we're not just simply interested in getting a picture to look the same, we're interested in getting the actual 3D representation of the scene. And then once it's done training, you actually have that 3D scene that we saw before, and you can use it in your simulation. So what is the output of a Gaussian splat? Well, as I mentioned before, it's simply a point cloud, right, that has attributes on it. It has position, orientation, scale, and spherical harmonics. As mentioned before, are view-dependent colors. And visualizing that inside of Houdini, without all the fancy shading tricks that you use when rendering it, we can actually see that once again, we have that exact same point cloud with disks attached to it, simply oriented in the right way so that when rendered, it looks as if it is the actual picture you took in real life. And that's it to Gaussian splatting. Now, it's a bit more complex than that, of course, but those are, in essence, what you do for Gaussian splatting. Once we've generated this splat, we actually need to do some post-processing before we can actually use it in product. And some of that includes merging tiles, right? Because if we do this at a very large scale, we can't simply process, tens of thousands of images on one single GPU. We tile this so that we can do it on multiple GPUs, for example, or do multiple tiles in sequence after each other on GPU. We then, of course, need to remove things like seams and make sure that everything fits together, and also do some additional metadata generation inside of Houdini, which we use in our simulation engine. One of the things that we do for cleanup is, for example, remove any Gaussians that collide with the ego. Ego refers to the vehicle that is actually driving through the simulation, because we know that there shouldn't be any Gaussians where we drove, right? Because there can't be anything. We drove on a road. So we use the camera trajectory, or extrinsics, as we've learned, to identify where the actual vehicle drove so that we can remove anything that would collide with the vehicle itself. Once we have our splat, we have our additional metadata that we've generated. All of that goes to product, where we're able to simulate inside of it. And so the pipeline, essentially, of the entire thing from start to what a customer can use starts with reconstruction, which we've just seen. Once we have our reconstruction, we are going to be creating a scenario where we can define what actually happens in this 3D environment. Oh, there's a car driving there, or a person is crossing a street, or we want there to be different types of road barriers, different types of road cones. We want there to be certain trees in the environment that we want to test. How would our car behave if there was a tree right there? So those are all things that you then define in the scenario. So really being able to essentially animate or simulate what happens in 3D space in the real world. And then you run the simulation, right? So you just have it play back as if it were actually happening for the vehicle, which then again produces video output that then, for example, perception models can use to train things with, or do whatever it is you want to really. And all of that is done at scale. So we can just run all of this automatically on the cloud to generate this automatically from, for example, a log, as it's called, from a data source that a vehicle provides us. And that's it. That's what we have to talk about today. Thank you.
We do have time for questions, so.
Hi, thank you. I'm curious about if you guys had thought about generating people in the environment or making them more dynamic, if that's part of the company plan.
Yes, yeah, that's also all already supported. Like you can, for example, one of the very important thing is vulnerable road users, VRUs. Because that's very important, right? What happens if a person suddenly runs across the street, or a cat, or some other animal? Can a model identify what it is and handle accordingly? So that's already supported and in the product that Joey was talking about. Yep.
Hi, great talk. I was wondering, when you place the white car inside the engine, I saw shadows on the bottom. How do you extract the lighting data from the scene from your images? Because maybe there are also street lights, maybe it's night. Yeah, that.
Yeah, so that's the interesting thing that we can talk about. But what I can say is that both the Gaussians and the synthetic actors we insert into the scene have bidirectional effects on each other. So the Gaussians can cast shadows on the synthetic actors we insert, as well as the synthetic actors casting shadows and lighting on the Gaussians themselves. Things like different lighting environments, that's something we're working on right now, because as you can imagine, if you're dealing with, for example, very hard shadows, or rain, for example, or night scenes, that poses very different challenges in a reconstruction, because suddenly you're dealing with very different sensor data.
Similar to that, how do you deal with the reflectance characteristic of Gaussian splats? Because when training on windows, they sometimes have like depth to them. Is that a problem?
No, so that's the interesting thing about spherical harmonics, as I mentioned, which means that it's view dependent. So when, for example, maybe you've seen that on one of the earlier slides where we saw me walking through that scene, when you walk around a shiny car, for example, you actually see the environment reflected on the Gaussians. And that is simply due to the nature of spherical harmonics, where the color changes on the angle. So it isn't really a reflection, it simply shows you the right colors from the right angle. So to answer your question, if you're dealing with buildings that are completely glass and you're trying to record inside of like a glass house or something, yeah, I don't know what's going to happen there. But windows and such on buildings, those are typically not a problem right now.
Thank you.
We have time for one more question. Yeah.
Yeah, thank you so much. Great talk. I was wondering, how long does the training process typically take, and how does it scale for larger scenes?
Yes, so the training process itself is actually quite fast. We started with a reconstruction of, I think if you take around 2,000 images, would take about an hour 40 for the entire process. That now roughly takes 15 minutes. So we've done some very significant improvements of what's out there with regards to Gaussian splatting. So to answer your question on scale, I mean, if you have cloud, you can do anything really. For example, while I develop this, I work locally on a 4090, which is extremely fast in terms of reconstruction as well.
Okay, thanks for the presentation.
Thank you.
Yep.